going to be talking about isomorphism. In terms of concept, isomorphism is actually not too bad. Let me give you a couple of graphs and use them to illustrate what we're discussing. Let's consider the following two graphs. These two graphs look a little bit different, but if you look at their edges, they're the same. For example, on the leftmost graph, A is adjacent to BCD, and on the rightmost graph, A is adjacent to BCD. So even though they look differently, they're really the same thing. We call them isomorphic. Let me give you one that's not quite as obvious. Let's take these two graphs here. So if we look at these two graphs, at least at first glance, they might appear to be different. If you look carefully, you might be able to convince yourself that they're more or less the same thing. In particular, if you were to look at the rightmost graph, this vertex T sticks out from a sort of kite shape, just like AB does, and SV sticks out just like DE. So both of these actually are isomorphic as well. But in order to say that they're isomorphic, we need to describe how the vertices match up with each other. For example, C should be treated like R. D should be treated like S, and so on. So what we do is define a function called an isomorphism. Some books use alphabetical characters like F. I prefer to use a Greek letter because if I use an alphabetical letter, it's very easy to accidentally label a graph vertex using the same letter of the alphabet that you're using for your function. So you can use F, H, whatever you want for the isomorphism, but I will use the Greek character phi. So phi of A is going to tell us what A to be paired up with. Well, a natural choice is to pair A up with T. If you look at this carefully, it turns out you could actually pair A up with V. There may be more than one choice, but the isomorphism has to settle on one of them. So this function phi tells you how to pair up the vertices of these two graphs in such a way that if a vertex on the left-hand side is adjacent to certain other vertices, then their images must also be adjacent. So in this case, C became R, B became Q, so that is next to R, F became U, which is next to R, and D became S, which is again next to R. So that means that if U and V were in edges of the leftmost graph, I'll call it E1, then the images of U and V are in the edges of the second graph, I'll call it E2. So everywhere there was an edge on the left-hand side, it gets turned into an edge on the right, and vice versa. Let's do one more example of this. So we have two different graphs here, and my claim is that they're isomorphic. Let me give them letters again. If these are isomorphic, then that means there needs to be a way for me to pair up vertices of graph G and vertices of graph H, do it in such a way that adjacency is preserved. So let's start by looking at something special about this figure. The common approach is to look for a vertex which has a unique degree, meaning that nothing else has the same degree. If you look at this, you'll notice that vertex G has degree 4. On the right-hand graph, T has degree 4, and nothing else does. So if these are isomorphic, then phi of G must be T, because they're the only degree 4 vertices. And then we can try to work from that point. So next to G, there is a degree 1 vertex, D. Looking at H, next to T, there is a degree 1 vertex, U. So D must go to U. There's another degree 1 vertex, A, but that's not next to G, so it can't be the one that's paired up with U. So we've covered these vertices. Now looking at what else is next to G, there is a degree 3 vertex, F. So looking at H, next to T, there's a degree 3 vertex, W. Now F and G were both adjacent to vertex E. So that means that their images have to be adjacent to something. Well, F went to W, and G went to T, and those are adjacent to Y. So Y is going to be the image there. Now we have B and C. The difference between these actually at this point is we have a degree 1, a degree 2, and a degree 3. So they're going to have to be paired up. We'll start with C, degree 2, and it has to go to S because that's the only option that's left, degree 2. And next to that, B, and that must go to degree 3, R, and then A, and A has to go to Q. So this is the isomorphism, and it tells us if you take the graph on the left, how do you pair it up with vertices on the right in such a way that adjacency is preserved?